Hello. Yeah, my name's Dan. So I'm just starting the second year of my NGD, and my research focuses on feasibility of extended reality in non-destructive testing. My industry sponsor is Amentum, which used to be part of Jacobs. So I'm not sure exactly where I fall in that category now, but all I know is that I work here at Manchester, and my supervisors are Anthony Payton and Jim Skelton, who you may know of. Um, I'm also part of the Fine CDT program, which has supported a lot of researchers over the years. And so, thanks to that, I have a fantastic cohort of colleagues who are working alongside me on other challenges related to NDE 4.0. Okay. Yep, yeah. So what do I actually mean by extended reality? Well, it's a bit of a spectrum. So on one end, we have virtual reality, which is, I think that's what most people are familiar with. Typically involves wearing a headset, and the key is full immersion. The user is sort of completely immersed in a digital environment. And this has been very popular in the entertainment or gaming industry for quite some time, but it's starting to expand beyond that. And so at the opposite end, we have augmented reality. And this is where the real world remains the focus, and the digital elements are just sort of overlaid on top of it. So a good example would be something like a heads-up display in an aircraft cockpit. That would be sort of augmented reality that is a little bit disconnected from the real world, just overlaid on top. And so somewhere in the middle of all that, you have mixed reality. And this is a term that's been around a while, but it's gaining a lot more popularity because the latest generation of devices are sort of marketing themselves as mixed reality tools. And I think it's quite an appropriate term because there is a significantly higher level of interaction between the physical and digital worlds on these devices, not just from the human side of it, pressing buttons, what have you, but also the digital interaction from the device itself. Um, and so listed on the bottom here are just some examples of different commercial devices and roughly where they lie on the spectrum. The Microsoft HoloLens 2, which is a few years old now, but that was a major push from Microsoft to bring XR away from entertainment and into industry. And it had a lot of success in healthcare and the military as well. This is sort of reflected in its design and form factor. It uses a transparent display so that you've always got this natural view of the real world. And the digital objects are superimposed using waveguides. This type of display is well suited for industry for sort of for safety reasons to maintain that peripheral vision. Very important. The more modern devices use a slightly different approach. So instead of transparent displays, they use high quality pass-through cameras, but can still switch to full VR immersion based on the activity that you're doing. And so this approach gives significantly better digital clarity, so the quality of the display. But the real world view is then, of course, limited by the quality of your cameras. And then lastly, sort of moving towards the VR end of the spectrum, I've got an example from HTC here, and that is a traditional fully immersive headset. And the only way that incorporates the real world is for safety reasons, really. It uses pass-through if you go too close to the edge, so you can sort of stay aware of your environment. Okay. Okay, so how does extended reality apply to NDE? Well, there's a lot. But my research focuses on the two key areas at the top. So that's visualization and tracking. Tracking is absolutely essential to everything in extended reality. We're sort of looking at how we can leverage the tracking capabilities to monitor the position of the probe, the user, and the component simultaneously. So this basically means that wherever an inspection is being performed, we can precisely record these positions, just like using mechanical encoders, but with less restrictions, more flexibility. The big advantage of this is that it allows us to visualize data in completely new ways. So I have an example on the top left here. This is one we did with ground penetrating radar in rack concrete. And yeah, we want to do this Superman X-ray vision where you can sort of overlay the data directly onto the material itself. So I'm going to talk a lot more about these two approaches later on. But scattered around the page, I've just got examples of how XR is currently used in industry and NDE. One major example is remote collaboration. Again, Microsoft made a big push in this area, effectively creating a high-tech version of Microsoft Teams. And this has seen widespread adoption in automotive industry, where during routine maintenance, you can have an engineer, maybe they encounter a problem, they need a second opinion. And so instead of waiting for a senior engineer to arrive, this person can remotely join the session, see through the engineer's eyes, and then even overlay 3D guidance into their field of view. I've heard through word of mouth that something like that has been applied to NDE as well, but there's some high-profile examples with the likes of Mercedes and other car companies. Similarly, we have step-by-step guidance. So AR can overlay instructions onto the real world that sort of shows the inspector what they need to do next. A really good example in NDE comes from a joint venture by companies Thornetics and Quasit. They were tasked with assisting pipe inspections by automatically overlaying a reference grid onto the component. Previously, they had to draw this on by hand. But the purpose of this was they then go step by step with their ultrasonic probe to make sure that they've got full coverage of the component. And there's also a company called Vuforia, who have developed platforms that allowed software engineers to build these kinds of guided environments. And they boast about the state-based feedback, which responds to what the user has already done. So, for example, if you're dismantling a car, the first step would be to lift up the bonnet. And then once the bonnet has been lifted up, the device can tell you what to do next based on what it can see. So really intuitive, really powerful stuff that has a lot of potential. So Exit is also being proven as a fantastic tool for training and education, and that applies to all ages. Because of course you have the ability to simulate environments or perhaps high value assets with no real expense. I've seen an example at BINDT of radiography training. So of course you can simulate the entire process with no real threat of radiation exposure. And it's been proven quite a number of times that these kinds of simulation can really drive up retention and engagement quite significantly, because it's a very immersive and memorable experience. And I have an extreme example of that in the bottom right, which is the Royal Navy built a full mission simulator. So this was a physical environment with screens and headsets and everything to mimic sort of mission scenarios. And so I think that sort of level of investment was a good indication that this is a worthwhile venture. And then looking ahead, with XR has potential with industry and NDE 4.0. We can integrate into robotic inspections. The example on the bottom left of using an iPad sort of approach, quickly see what the robot is going to do next, or what the data looks like. And then it's an avenue into machine learning as well, because when we can index data with position, that can offer a lot of benefits for pattern recognition and things like that over the long term. So a lot of integration with other key areas of research as well. Replace that. And and so just one sort of message we want to maintain throughout our work on XR is we're not trying to force change where it isn't needed. I think there are plenty of situations where the existing technology like traditional screens and equipment work perfectly fine. And this is a challenge for XR industry as a whole. The key is to find a case study where XR really adds value. And I think NDE is a great example of that, because there's lots of situations where the hands-free displays, the intuitive data visualization could have a really positive impact. But that's the key. It's using the right tool for the job. So before I dive a bit deeper into my work, I think I'll just introduce sort of how these devices work. And most headsets work in a similar way, but I've just chosen the HoloLens again here. The core component is tracking. So it uses a combination of cameras, wide-angle cameras and sensors, which all kind of serve specific functions. Some cameras are dedicated for hand tracking or for eye tracking, things like that. But then you may also use like a LiDAR sensor to get a measure of depth. They also commonly use inertial measurement units, so like accelerometers, gyroscopes, because they help to compensate for motion blur and can ensure, maintain smooth tracking even when, the headset is moved quite quickly, or if the camera feed, loses its clarity. So that combination of sensors works really well together. Sorry, that's back. And then, so yeah, of course, all of this requires processing power. And this is probably something I'm going to mention quite a few times throughout the presentation. But a big problem for wearable tech is you have to do this in a smaller form factor and carefully measure your power consumption and your thermal regulation as well. And so, yeah, that's optimizing performance is while keeping the devices lightweight and wearable is a constant challenge for the entire field. And closely related to that, you have the display itself. So since these headsets sit so close to our eyes, you have to render the images at very high resolutions and refresh rates to prevent motion sickness. This again sort of makes them more computationally demanding than traditional displays. But at the heart of all of this is an algorithm called SLAM. And this stands for simultaneous localization and mapping. And so what SLAM does is it allows the headset to continuously scan and reconstruct its environment into a 3D model in real time. So a good way to visualize this is like, imagine taking your room and throwing a white blanket over the top of it, and then how it sort of conforms to all the creases and edges. That's sort of what SLAM is doing with a digital mesh. And so I've just got an image of that on the right-hand side. So the top image is the normal view, and then the one below that shows how this mesh sort of conforms to the characteristics of the room. And so, yeah, the key takeaway from this slide is that the devices are capable of constantly reconstructing the environment over time. And it turns these vertexes into digital reference points, so it knows where to hang digital content in a sort of intuitive way. Okay, so what we specifically want to achieve is the ability to track the position of the probe, the component, and the user simultaneously. The reason for this is because it allows us to significantly enhance the data visualization, and it's a general path to digitization of NDE processes in general. But by indexing all the scan data permanently, you can correspond that with a digital twin, for example. And so you can build this much more intuitive representation of the inspection results, permanently store it, and share that information however you like. So the current competitor is sort of traditional encoders. Just have an example of the Olympus map scan over there. And these are great, but they are expensive, and they usually can only track movement in 1 or 2 axes at a time. With XR, we can do 6 degrees of freedom, which means we get all axes in translational and rotational movements simultaneously. So yeah, in contrast to the Olympus map scan, which can do 2 axes there, and it can stick to the pipe directly, but incurs a massive physical restriction on top of that, and it's quite expensive bits of kit as well. So potentially a lot to gain by optical tracking methods. Yeah, so I think that this approach to digitization, paths to machine learning, temporal modeling, things. I think this really well aligns with the overall objectives of Industry 4.0. But okay, so how do we actually do this? Well, the technique I'm most interested in is called visual inertial odometry, which is the fusion of optical and inertial units to return position information. This is widely used in extended reality because the sensors complement each other very well. And a typical solution for VR controllers is to use an infrared marker-based system, a process known as constellation tracking, which sort of combines blob detection with pattern recognition to return the position of the controller at any point. But I'm keeping my options open. A more traditional method of tracking uses fiducial markers. So like here in the bottom right, it's like a QR code April tag sort of approach. And these can serve as prior known fixed reference points in space. And it uses more traditional approaches like edge and line detection, comparing it to the model it knows it should be looking for. But we also have hand tracking. Hand tracking is very popular, again, as an interaction method in VR. And this typically uses sort of machine learned models to recognize the digits. And there is some really interesting research in this area. The image in the top right is a setup from a paper by a team that looked at a slightly older version of the technology, but this was in an NDT ultrasonic context, and it's probably one of the best examples of data visualization that I've seen. So yeah, I'd really recommend this paper if anyone's interested in sort of the pinnacle of the research. But it's also very popular in the medical sector. I've seen a lot of examples of where VR has been tested to measure sort of stroke rehabilitation, so measuring how well the rotation of the limbs works after a patient has suffered a stroke. Yeah, so lots going on, but like I say, the technology moves so quickly, it's important to stay on top of the modern advancements. And so that leads me to my next slide. Yeah, so the challenges of object tracking. The key thing is the current commercial products are designed for they're built for purpose. They're designed for VR applications, and so this prioritizes speed and quite wide ranges of motion. But for NDE, we don't necessarily need that because it's a much more controlled a much more controlled process, meaning we don't need these extreme responses, but we do care about precision, accuracy, and stability. So because of this, a major part of my research is evaluating the capabilities of the existing tracking solutions, which are not quantified well at all. There's usually just a vague statement about high accuracy and absolutely no numbers to back it up whatsoever. And it's also the values are always a function of the use case and the environment. So there's a lot of unknowns to figure out first. And as I mentioned before, yeah, the sector moves so quickly, you need to use the modern tech. A great example of sort of the approach we want to take is in this Logitech tool here at the bottom. This is a brand new VR accessory just released last year, and it condenses the infrared constellation tracking technology into a form factor that's not much bigger than a normal pen. And so it's been designed for more precise applications like digital writing. And so it sacrifices some range of movement, but allows for more controlled sort of fine motor interactions. And that approach is exactly what we want to do for NDE. Exactly. So, just focusing on accuracy, precision, and stability. And these other two images are just other examples of tracking components. Instead of using infrared, they have cameras in themselves, and so they sort of self-track. They do their own version of SLAM to position themselves in 3D space. HTC in particular have released quite a few of these designed for body tracking in VR. But then, of course, our old friend, the processing limitations, we have to balance these capabilities with processing and optimize it to reduce latency and things like that. So I know that some of you might be thinking, if these devices can map their entire environment in real time, what is happening with all that spatial data? Well, this is a very important concern because there may be situations where we don't want that spatial data to go walkabouts. And the good news is, for performance reasons, these processes usually run locally on the devices, meaning no internet connection required. So the data doesn't have to leave the headset. But there are examples that do. So there's sort of shared spatial anchors approaches, which may use cloud computing to store that information. And so these types of things are things we have to think about very carefully to make sure we maintain full control over the data lifecycle, because otherwise there could be serious security implications. Okay. Okay, so now that we've got perfect, robust tracking, we can take full advantage over the enhanced data visualization. So scattered around this slide are examples of work that we've done at Manchester over the years. One example is the ground penetrating radar that I mentioned earlier. This was on some rack concrete. I think I remember there was a big uptake in the interest of rack inspections when we realised the schools were about to fall down. That was an interesting piece of British media. And yeah, we were able to overlay the scan data directly onto the sample in real time. But earlier in my career, we worked on a landmine detection project where we built a device that included a camera module for continuous position tracking. And so this allowed us to map the detector's movements against a known reference on the ground, which could create a heat map of the scanned areas. And this approach had huge benefits sort of when scaling up inspections over large fields, because it was crucial to have a system that lets you revisit the known reference points and sort of analyze all that data very systematically. But we also managed to integrate it into the existing process. So there was virtually no difference between what the workers were doing before we introduced this new technology. It was just a digitization step. In the bottom left corner, okay, so this is a demo that I'm show a video of in a few minutes. But I've connected an ultrasonic acquisition system to a mixed reality system. And this is just doing some real-time visualization of the data there. So I'll go into more detail on these two on the next few slides. And just on the bottom right, there's an example from a fellow researcher at Manchester. Roxwan is looking at augmented reality for eddy current applications, and he's looking more carefully at marker-based tracking. So you can see in this image, he has sort of 4 reference points in the corners, and then uses a 5th to track the probe. And the advantage of doing it that way is you can get very good accuracy. So on a small scale like the plate he has there, you can still return really well indexed data. Okay, so so I mentioned I've got a video to share, so just introduce what's going on there. This is the first steps towards a fully functional system. So I'm sort of just getting the NDT pieces connected to the mixed reality tech. So on my desk, I have a test pipe where I can run a phased array probe along the surface. And the goal is just to perform a basic wall thickness estimation and map any potential areas of interest in thickness of along the pipe as we go. So the probe is connected to a micropulse system that does some of the collection and processing. And the first part shows sort of graphical views, but the second part is quite interesting, where we leverage the position tracking from the Logitech pen that I mentioned earlier, and we use that to index against the pipe, or sorry, rather a digital twin of the pipe, and then we can virtually project the data on top of the pipe. Okay, yeah, so let's move on. So apologies, it does have more of me speaking, but I'll just let this play. This is a demonstration of the XR inspection application. which connects an ultrasonic acquisition system to a Meta Quest 3 headset. The system can be controlled directly from the headset, and the signals are represented as A scans and B scans in real time. The display can be placed anywhere at the user's discretion, either by grabbing hold of the screen or adjusting it from a distance. By toggling the switch, the data streams in real time with minimal latency. Even in this simple form, it has a distinct advantage over traditional monitors, which are limited by physical size and weight. The Logitech MX Ink stylus is a new accessory that can be used in place of the traditional controllers. It also facilitates 3D sketching, so the user can leave notes or mark areas in the digital environment. In an NDE context, this may be used to record the position of defects directly onto the component, so that this information can be permanently stored and shared as a digital twin. By fixing the stylus to the probe, we can use its position information to demonstrate the potential of ultrasonic XR. The signal response can be painted onto the digital twin as a heat map, where hotter colours indicate variations in thickness or liftoff. When I lift the probe away from the component, the system warns me that the area has been improperly scanned. Finally, this data can be permanently indexed onto the digital twin, which can be stored for further review or shared with another system. Pass-through video can be enhanced to improve our perception of reality. In this example, a filter is applied to highlight the edges of objects. Tactical use of this method could offer a solution to challenging problems like occlusion and depth perception in extended reality. Oh, sorry, did the sound cut out for everyone there?
It just cut out on the current image. It's been fine, Dan.
Oh, it's my end.
We've had all the sound. We got all the sound in the video.
Sorry, seems I'll just leave this playing. Sorry, there's a problem with my sound at this end.
It seems to have suddenly lost the sound for some reason at this point. I think it's frozen, hasn't it? The movement of the was at the end of the video.
Oh, sorry about that. It seems my sound just completely cut out then. Not sure what happened. But yeah, sorry, Martin. Could I just check? Did most of the video play okay? Or have I? Okay. I will. Okay. Okay, cool. So my sound is still coming through. Okay.
Fine, yes. Yeah, and people in the chat have said they can hear it fine.
Oh, good.
Great.
Yeah, yeah. Sorry about that. That must have been a problem. My headphones or something. It just completely cuts out, just doing its best to embarrass me. Okay, so yeah, so this is a good chance to talk about some of the challenges with data visualization, and the processes we choose to use. So at the center of all this work, you have the human user. And so the comfort and usability of these systems always have to be a top priority. Motion sickness and eye strain are major concerns for all XR applications. And the way we present visual data needs to be intuitive, but also physically comfortable to look at for a reasonable amount of time. So sort of things like visual overload is a real issue. You don't want to throw too much at the user because they can feel sort of a little bit claustrophobic almost. And I mentioned before that we don't want to put a headset on everyone. We want to use the right tool for the job. But we also don't want to trap people in headsets. So even when the technology is beneficial, the user should always have the ability to sort of quickly switch between the real and the virtual worlds. So yeah, very relevant to what I'm doing. The challenge of depth perception is really difficult. So this is a screenshot from the video that you just saw. And you can see how we're attempting to do this Superman X-ray vision, but there's some issues with occlusion mismatch. And that's because your brain primarily uses occlusion as a measure of depth. But when we start overlaying semi-transparent or see-through objects, those cues get disrupted, and it can create a bit of a psychological confusion where your brain knows something is not quite right, and that can lead to headaches and eye strain and just general discomfort. So this is a very significant issue, and it's one we pay attention to, but we're more concerned with tracking. So it may not be my responsibility to find an optimal solution as part of my research, but it is an important ongoing problem for the wider industry. Yeah, it's not fully understood, and it's subtle details that make a really big difference. But yeah, on that note, we have made some progress in that area. These two images at the top show an earlier version of the rack inspection. So this first one, version 1.0, shows a 3D model approach, where we've put the 3D geometry into the Unity engine, and that's very limited. Quite difficult to do clever things with that. But a much better approach is to mimic the way that data is processed in medical imaging, and like CT scans, that sort of thing. And it uses a volumetric rendering approach called ray marching, a little bit similar to ray tracing. And what's interesting is there is no three-dimensional data there at all. All of these points have been colored based on the data values inside. So we can define a transfer function to really improve the way the data looks. So that has gone a long way to solving some of the problems, but again, comes back to the optimization problem. Okay. And yeah, so just to finish up, just taking a brief look into the future. So my personal objectives are to design, test, and measure the effectiveness of some of the commercial XR products for NDE applications. And that's with a view to publishing these, of course. But the key takeaway sort of from the presentation is that while extended reality has really significant potential, we need a deeper understanding of how all these tools perform in real world inspection environments before we can sort of converge on an optimal solution for NDE. But then just considering the broader trends in the industry, the whole industry for a long time has been pushing towards reducing the form factors of this technology. One of the most interesting developments in this space is Meta's Orion glasses. And these are sort of the first AR glasses, true AR glasses prototype that represent a real shift into the direction the industry wants to go. All about making this sort of approach is what will make them much more ubiquitous. And just if we compare that to sort of the developments over the the past 80 years. This was the first AR headset by Ivan Sutherland, and it was nicknamed the Sword of Damocles because it was so heavy it had to be suspended from the ceiling. So yeah, this trend will definitely continue into the future as it picks up interest. But another key trend is to sort of break free from the gaming stereotype. So XR, as I've mentioned, has long been associated with entertainment, but companies like Microsoft and Meta are actively working to reposition XR as a serious productivity enhancing tool for all sorts of industries. And I think our work in NDE fits directly into that shift, and NDE is a great opportunity for it to thrive. So that's it. I think that is the end of my presentation. Just I'll leave the summary slide up, but I am happy to take any questions.
Great, thanks so much, Daniel. That's a very extensive overview of all that's possible with XR, and this idea of superimposing NDE data on the samples in real time is something that people always look for. I'd like to ask Ikesh to give the first question.
Thank you, Martin, and thank you, Daniel, as well. Excellent overview, and like the last photograph that you've shown, how it has evolved from 1968 till now. Daniel, looking at all this, the data and information that you have shared, especially a couple of cases that you explained, I understood all this has been captured in the laboratory environment, not in the field condition. So my question is, how you rate this technology in terms of TRL level readiness? Is it ready to straight away deploy in the field, integrating with existing NDT application?
It depends on the specific application. So some of the stuff that I mentioned earlier that Microsoft has worked at, like the remote collaboration, that is at a very high TRL level because it's building on existing software and works very well. In the NDE examples I've shown are much lower. Yes, so it's just emerging technology because there's quite a few problems. So one is scaling it up to match the potential of NDE inspection. So using mine as an example, it works with one very specific configuration for my pipe, and so obviously you want to build in like something where anyone with UT experience can come in and apply any configuration, phased array, full matrix capture, all of those kinds of things, and do whatever they would normally do in an NDT process, but just with the AR as a benefit. So yeah, there's lots of work to do in all areas, basically.
Thanks, Anya.
Great. It's a question from Susan Osbeck from Sonmatic. It looks like a great system to improve manual UT or manual corrosion mapping collection, but automated scanners take away dull physical work from the technicians. Using this kind of track system puts back the physical requirements of the job. How accurate and repeatable is the localization?
Okay, so to directly answer the accuracy question, what I've done so far is gone through all the existing literature to try and find a value. And it's very dependent on the use case and the environment that it's in. Particularly the lighting plays a big role. But what you typically see is you can get to about 2 millimeters before the percentage error starts to increase quite significantly. So it's very good at larger movements. And yes, starts to fall off at incremental steps like 1 millimeter steps. That is of course because it's designed for human motion body tracking, and up until recently hasn't had any interest in these smaller movements. So that's where we want to come in and see if we can adapt it to fill that gap. But to answer your question with automated scanners taking over the dull manual inspections, we're not trying to replace those systems. There will be instances where the robotic systems are superior and you can bring mechanical encoders in, and an AR would not be the right tool for the job. You may want to use AR in a different capacity. So if I might just scroll back a few slides. Thinking about this image in the bottom left, you can see a manager is sort of using an iPad to get a quick overview of where the systems are at. That sort of approach can be really effective with robotics because you can effectively see through the robot's eyes. So yeah, like I say, it's all about choosing the right tool for the job and not trying to force the technology on people. Yeah, that's.
Yes, no, that's a great thought. I mean, in terms of NDT techniques, which are the ones you see as being most useful for early application? I was thinking of things like phased array AUT or digital radiography or that type of thing.
Yeah,
digital
well,
radiography can be complicated, yes, but
yeah, exactly. It depends on the data flow. So you need to be able to get data into the system. So the electrical methods, ultrasonics, eddy current are very easy to port across. But there's lots you could do. Thermography I think would fit very well. But there's another person in my cohort working on vibrational systems. So yeah, you could go down these more niche aspects as well. I personally quite like UT because you get the depth as well, and that's particularly good for visualization because you can see into the component. You can do the X-ray vision effect much better with depth information. But yes, it's a really good point because we're trying to build these systems with the view that anyone who wants to come and plug in their technology will be able to at a future date.
I think I can see with corrosion mapping, for example, as Susan mentioned, that could be a very good visual way of sort of speeding up the fast screening of components if you're able to superimpose the data, and so they're actually seeing like a corrosion map from carrying out the manual measurements. I think that could be quite effective.
Yeah.
Great. Yes. Yeah, no, thanks. That's a very extensive overview.
But yeah, no, thanks very much for the opportunity. Yeah, I hope everyone found it interesting.